All right, gentlemen, as we start inching our way closer and closer to statistics, we turn our eyes towards probability. So in probability theory, there's certain things that have to be true for us to make sense of what's going on. And I have the summer notes pulled up here, and I'd like to discuss some of it. So perhaps the most important sentence in this entire document is this right here. I guess not even sentence, clause, right? Because it's true. As human beings, we do not have a natural inclination towards studying probability accurately. We tend to be much more prone to mistakes when it comes to probability. So the most natural example of a probability problem is tossing a coin, right? And we'll call it a fair coin if there's a 50-50 chance of it being heads or tails. And here's where we need to start talking about probability. We say 50-50 chance. What we really mean is that the probability of heads is equal to 1/2. All right, so the thing with probability is that our probability is always less than or equal to 1. 1 is our version of 100%. And we always want numbers less than or equal to 1. And we need numbers greater than or equal to 0. All right, so tossing a coin, the probability of heads is 1/2. And we also have the probability of tails is 1/2. Okay? And we'll talk a little bit later today about this, but what's important is that these are all the possibilities, and if I add them together, I get 1. So for our function to be a probability function, we need to add up to 1. And we'll talk about that again later. All right? So here is one of the basic fallacies of probability. Say I toss a coin. I toss it 100 times, and from the 100 times in a row, I get 100 heads. Is the 101st toss more likely to be heads or tails? So what people tend to say is kind of in a naive way that it is, right? Because we expect it to be 50-50. The first 100 were all heads. We got to start getting closer to 50-50. So we should have a tails next. And that's not true. That's not true. So what we say is, for this example, tossing a coin is an independent. I can't fit that. Can I move it over? Nope. Let's write little. Independent event. Right? So independent events don't depend on what happens beforehand. So just because I flipped a coin 100 times in a row and it got all heads doesn't mean anything about the 101st coin toss. In other words, the coin does not have a memory. It doesn't know what happened beforehand. Right? And that's a mistake to assume that it will. What does happen, though, is eventually things start to even out. Right? The long-term behavior will eventually overcome any short-term randomness that leads to skewed data. So, right, like if the first 100 tosses were all heads, but if I toss a coin like 5 million times, it doesn't really care what the first 100 tosses did in the grand scheme of things. It doesn't skew the numbers much. So eventually, we tend towards the expectation or the expected value. And that's what we mean by probability. So we say if we flip a coin that it comes up heads 1/2 of the time, means that if I repeat this experiment forever, we expect the probability of getting ahead, we expect the number of heads to be around half. Okay? And this is what we have written down right here. Okay, so we need some special terms. First term, if we're doing an experiment, kind of like tossing coins here. Experiment here like tossing coins. We have something called a sample space. Sample space, in our case it's heads and tails, right? We have a sample space. If we were rolling dice, it'd be the numbers 1, 2, 3, 4, 5, 6, right, for one die. And an event is just a member of the sample space. All right, an event is just a member of the sample space. So this sample space has two events, heads or tails. And we say the probability of an event is the value that its relative frequency of occurrence approaches in the long run. There's limits and stuff here. But we can make sense of this in a practical matter. Right? And the second bullet point, this third, I don't know, whatever bullet point we're up to, talks about that, right? Since we have two equally likely outcomes, heads and tails, their probability is both 1/2. And the important part about this is that they are equally likely to occur. Okay? All right, so here is some problems that I'd like to discuss. And here's how I think about probability. I kind of think of probability as combinatorics divided by combinatorics. What do I mean by that? Is we count two things and we divide them. All right, we count two different things and we divide them. What do we count? We count our sample space, that goes in the denominator, and then we count the number of things we want to happen, and that goes in the numerator. So let's think about A. We want to toss two heads in a row on two tosses of a fair coin. So how many ways did it toss a fair coin? Twice? Well, it's tails, 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 heads, heads, tails, heads, heads. It's the four options there. Okay, so we have an answer here, but the way I think about this is my sample space has size 4. Okay? And how many of them are two heads in a row? Well, there's 2 of them. Heads, heads. There's one of them, heads, heads. So this is going to be 1/4, just like we have in the notes. Okay? Drawing a queen from a standard deck of 52 cards. Right? Standard deck, if you remember, there are 4 queens in a deck of cards. So I write down the sample space. How many ways can I draw one card? Well, there's 52 ways. How many of them are queens? There's 4 of them. 4/52 is 1/13. Okay. Rolling a sum of 4 on a single roll of 2 fair dice. 2 fair dice, we talk about the multiplication principle of counting. There are 36 equally likely outcomes. if we roll 2 dice. One way to do it is just by using multiplication principle. Another way to do it is I can actually write them all out. I can get 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 2 1, 2 3, 2 2 1, 2 2, 2 3, 2 4, 2 5, 2 6. We go on. We get 6 1, 6 2, 6 3, 6 4, 6 5, 6 6. We want to know how many ways there to actually get a 4. And if you look at this chart, it's actually this diagonal. There's only 3 ways to get a 4 if we roll 2 fair dice. So this is 3 over 36, which is 1 over 12. Again, 36 is the size of my sample space. 3 is the number of outcomes that I care about. Okay, and now D is a little weird, right? Let's think about it. It's not going to be 1 in 4 because we already know you have tendinitis, right? Right? It's not going to, we already know that you have tendinitis. Right? So having tendinitis, if your doctor tells you that further tests are needed to determine whether your sore knee is caused by tendinitis, bursitis, arthritis, or a torn meniscus, since we already know you have tendinitis, we cannot do this. I'll put a sad face on this. We cannot do this with the methods we have at our fingertips right here, and we will talk about them at a later time in the course. Okay? So, let's do this example here. Rolling the dice. Find the probability that the sum is divisible by 3 on a single roll of 2 fair dice. We need to figure out how many ways we could be divisible by 3. Well, how many ways can I get a 3? That's 1, 1, 2, or 2, 1. How many ways can I get a 6? That's 1, 5. 2, 4, 3, 3, 4, 2, 1, 5. How many ways can I get a 9? That's 5, 4, and I guess we should do 3, 6, 4, 5, 5, 4, 6, and 3. And 12 is just 6 and 6. So how many ways are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 12 over 36, which is 1 over 3. Okay. All right, and now the last thing I really want to talk about here is there's a lot of information in here. Here's a good place to put it. It's a probability function. Okay? So we're going to let S be a sample space. Let S be a sample space of events E1, E2, E3, say En, right? So we have finite number of events, that's fine. It can be infinite, but just for our, we'll talk about how it can be infinite later. A sample, right? P is a probability function if P of EI has to be bigger than or equal to 0, but less than or equal to 1 for all I. And what does this mean? That no matter what E1 or E2 or E3 or En, no matter what E I plug in, the answer is going to be between 0 and 1. And I can write probability of E1 plus probability of E2 plus probability of N is equal to 1. When we add them all up, we need to get 1. Okay? Another way of saying this, in our fancy notation, probability I equals 1 to N, sum of I equals 1 to N of the probability of EI is equal to 1. Okay, those are two different ways of saying it. So here's a little bit of information about probability. I'll give you some practice problems to work on this, and we can talk about it next time we meet.